According to the National Electrical Code, specifically Article 250.52, A5, all buildings, including isolated outbuildings, are required to have a grounding electrode system. However, there is an exception to this requirement. Only one grounding electrode system is required for multiple isolated buildings in the same property that have no interconnecting plumbing, heating, or air conditioning systems connected to the grounded conductor. This exception is detailed in NEC 250.53. B1. If an accessory building has no plumbing connecting it to the main house, the exception applies, and there is no need to install a separate ground rod. In cases where an inspector requires the installation of a local ground rod, it is likely based on local code requirements or their own interpretation of the NEC. The NEC, however, allows for the exception as mentioned before in section 250.53. B1 for isolated outbuildings. There is no inherent safety hazard in grounding the accessory building from a sub-panel as long as the grounded conductor is installed according to code. Ground loops can occur when multiple ground paths exist, but this is not the case when following the NEC exception for isolated outbuildings. If faced with an inspector insisting on a separate ground rod, providing them with a copy of the NEC section 250.53. B1 can help clarify the situation. If they still insist on a separate ground rod, requesting a written explanation of their reasoning is advisable. NEC 250.52. A5 dictates what can be used as grounding electrodes. These electrodes are things like metal underground water pipes, metal and ground support structures, concrete encased electrodes, ground rings, and rods and pipes. More specifically, 250.52. A1 describes metal underground water pipes where the pipe is in direct contact with the earth for 10 feet or more, and is electrically continuous. This section also stipulates that the metal water pipe must be supplemented by an additional electrode of a type specified in 250.52. A2 through A8. 250.52. A2 describes metal and ground support structures. This requires an in-ground metal support structure that is in direct contact with the earth for 10 feet or more, bonding it to the grounding electrode conductor. 250.52. A3 describes concrete encased electrodes, which consists of at least 20 feet of bare copper conductor, not smaller than 4 AWG, encased within at least 2 inches of concrete, and located within the bottom of a concrete foundation or footing that is in direct contact with the earth. 250.52. A4 describes ground rings, which requires a bare copper conductor not smaller than 2 AWG, buried in the earth at a depth of not less than 2.5 feet, that encircles the building or structure. 250.52. A5 covers rods and pipes, which are electrodes of rod and pipe type that shall not be less than 8 feet in length and shall consist of either A, an iron or steel rod that is at least 5/8 of an inch in diameter, B, non-ferrous rods that are listed and are at least 1/2 inch in diameter, or C, a steel or iron pipe that is at least 3/4 of an inch in diameter. 250.52. A6 describes other listed electrodes, which allows for other listed grounding electrodes to be used. 250.52. 87 describes plate electrodes, which consists of a metal plate electrode that exposes not less than 2 square feet of surface to exterior soil. Iron or steel plates must be at least 1/4 inch thick, while non-ferrous metal plates must be at least 0.6 inches thick. Finally, 250.52. A8 describes other local metal underground systems or structures. This includes underground systems, piping, and tanks. Grounding electrode systems are vital for electrical safety. They provide a low impedance path for fault current to return to the source, which helps to trip over current protection devices like circuit breakers or fuses, thus preventing electrical shock and minimizing the risk of fire. Grounding also helps stabilize voltage to ground during normal operation, preventing voltage surges and ensuring proper operation of sensitive electronic equipment. In general, installing a grounding electrode system involves driving ground rods into the earth or connecting to a metal water pipe that is in contact with the earth for at least 10 feet. The grounding electrode conductor, which is typically made of copper, connects the grounding electrode to the grounding busbar in the electrical panel. All metallic parts of the electrical system, such as metal conduit, enclosures, and equipment grounding conductors, are bonded to this grounding busbar. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. For example, if the service entrance conductors are 2/0 AWG copper, the grounding electrode conductor must be at least 4 AWG copper. In specific scenarios like isolated outbuildings, the NEC provides exceptions that must be carefully considered. As mentioned before, NEC Section 250.53 B1 allows for a single grounding electrode system for multiple isolated buildings on the same property, provided that there are no interconnecting plumbing, heating, or air conditioning systems connected to the grounded conductor. This exception recognizes that interconnected metallic systems can create multiple ground paths, which can lead to circulating currents and potential safety hazards. When applying this exception, it is crucial to ensure that the grounded conductor is properly sized and installed, and that all metallic parts of the electrical system are properly bonded. It is also important to communicate with the local electrical inspector to ensure that they are aware of this exception and that they agree with your interpretation of the code. Ground loops can occur when there are multiple ground paths between two or more pieces of equipment. These multiple paths can create circulating currents, which can cause noise, interference, and even equipment damage. In a properly grounded electrical system, there should only be one path to ground, which is through the grounding electrode conductor to the grounding electrode. When multiple ground paths exist, they can create a loop, which can act as an antenna, picking up electromagnetic interference and injecting it into the electrical system. To prevent ground loops, it is important to ensure that all equipment is properly bonded to the grounding busbar in the electrical panel and that there are no unintended ground paths. This can be achieved by using a single-point ground system where all equipment is grounded to a common point. It is also important to avoid using multiple grounding electrodes, as this can create multiple ground paths. In the case of isolated outbuildings, the NEC exception for a single grounding electrode system helps to prevent ground loops. The grounded conductor, also known as the neutral conductor, carries current back to the source in a single-phase alternating current system. It is typically identified by a white or grey color. The grounded conductor is connected to the grounding busbar in the electrical panel, which is then connected to the grounding electrode. In a properly grounded electrical system, the grounded conductor should only carry current during normal operation. During a fault condition such as a short circuit, the fault current should flow through the equipment grounding conductor back to the source, tripping the overcurrent protection device. It is important to ensure that the grounded conductor is properly sized and installed, as it can carry a significant amount of current. The size of the grounded conductor is determined by the size of the ungrounded conductors, as specified in NEC Table 220.61. It is also important to ensure that the grounded conductor is properly bonded to the grounding busbar, as this provides a low impedance path for fault current to return to the source. The equipment grounding conductor, also known as the ground wire, provides a low impedance path for fault current to return to the source. It is typically identified by a green or bare color. The equipment grounding conductor is connected to the metal parts of electrical equipment, such as enclosures, conduit, and motors. During a fault condition, the fault current flows through the equipment grounding conductor back to the source, tripping the overcurrent protection device. It is important to ensure that the equipment grounding conductor is properly sized and installed, as it can carry a significant amount of current. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device, as specified in NEC Table 250.122. It is also important to ensure that the equipment grounding conductor is properly bonded to the grounding busbar, as this provides a low impedance path for fault current to return to the source. Bonding refers to the practice of connecting all metal parts of the electrical system together to create a low impedance path for fault current to return to the source. This includes metal conduit, enclosures, equipment grounding conductors, and the grounding electrode conductor. Bonding is essential for electrical safety, as it helps to prevent electrical shock and minimize the risk of fire. When all metal parts of the electrical system are properly bonded together, they are at the same potential, which means that there is no voltage difference between them. This prevents electrical shock in the event of a fault condition. Bonding is typically achieved by using bonding jumpers, which are short lengths of wire that connect metal parts together. Bonding jumpers are typically made of copper or aluminum, and they must be properly sized to carry the maximum fault current. The size of the bonding jumper is determined by the size of the overcurrent protection device, as specified in NEC Table 250.102. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect against electrical shock. They work by monitoring the current flowing in the circuit and detecting any imbalance between the hot and neutral conductors. If the GFCI detects an imbalance of 5 mA or more, it will trip the circuit, cutting off the power and preventing electrical shock. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. They are also required on all 125-volt, 15 amp and 20 amp receptacles in dwelling units. GFCIs are available in several different types, including receptacle type, circuit breaker type, and portable type. Receptacle type GFCIs are installed in place of standard receptacles, while circuit breaker type GFCIs are installed in the electrical panel. Portable type GFCIs can be plugged into a standard receptacle and provide GFCI protection for any equipment plugged into them. Arc fault circuit interrupters, or SIs, are devices that protect against electrical fires. They work by monitoring the current flowing in the circuit and detecting any abnormal arc conditions. Arcs can occur when there is a loose connection, damaged wiring, or a frayed insulation. If the SI detects an arc, it will trip the circuit, cutting off the power and preventing an electrical fire. SIs are required in many areas of the home, including bedrooms, living rooms, and dining rooms. They are typically installed in the electrical panel and provide protection for the entire circuit. SIs are available in several different types, including branch circuit type and combination type. Branch circuit type SIs protect against arcs in the branch circuit wiring, while combination type SIs protect against both branch circuit arcs and series arcs. Overcurrent protection devices, such as circuit breakers and fuses, protect against overloads and short circuits. They work by monitoring the current flowing in the circuit and tripping the circuit if the current exceeds the rated value. Circuit breakers are reusable devices that can be reset after they trip, while fuses are one-time devices that must be replaced after they blow. Overcurrent protection devices are essential for electrical safety, as they help to prevent electrical fires and equipment damage. They are required on all electrical circuits and must be properly sized to protect the wiring and equipment. The size of the overcurrent protection device is determined by the ampacity of the wiring, as specified in NEC Table 310.16. Electrical inspections are conducted by qualified electrical inspectors to ensure that electrical installations comply with the NEC and local codes. Electrical inspectors check for a variety of things, including proper wiring methods, proper grounding and bonding, proper overcurrent protection, and proper installation of electrical equipment. Electrical inspections are typically required for new construction, renovations, and repairs. They are also required when electrical service is upgraded or modified. Passing an electrical inspection is essential for ensuring the safety of the electrical system and obtaining a certificate of occupancy. When dealing with electrical inspectors, it is important to be respectful and professional. It is also important to be familiar with the NEC and local codes so that you can answer their questions and address any concerns they may have. If you disagree with an electrical inspector's decision, it is important to remain calm and explain your reasoning. You may also want to consult with a qualified electrical contractor or engineer to get a second opinion. Always remember that the electrical inspector is there to ensure the safety of the electrical system, so it is important to cooperate with them and address any issues they may identify. The National Electrical Code is a comprehensive set of standards for the safe installation of electrical wiring and equipment. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC is adopted by most states and local jurisdictions in the United States and is used as the basis for electrical inspections. The NEC covers a wide range of topics, including wiring methods, grounding and bonding, overcurrent protection, and equipment installation. It is essential for all electrical contractors, electricians, and electrical inspectors to be familiar with the NEC. The NEC is available for purchase from the NFPA and other sources. It is also available online through various subscription services. Staying up to date with the latest edition of the NEC is essential for ensuring the safety of electrical installations. Electrical safety is paramount when working with electricity. It is important to always follow safe work practices and to use appropriate personal protective equipment, or PPE. PPE includes items such as rubber gloves, safety glasses, and insulated tools. Before working on any electrical equipment, it is important to de-energize the circuit and verify that it is de-energized using a voltage tester. It is also important to lock out and tag out the circuit to prevent it from being accidentally re-energized. Never work on electrical equipment while standing in water or on a wet surface. Always assume that all electrical equipment is energized and treat it with respect. If you are not qualified to work on electrical equipment, hire a qualified electrical contractor. Electricity can be dangerous, so it is important to take all necessary precautions to protect yourself and others. Understanding voltage drop is crucial in electrical installations to ensure that electrical equipment receives the proper voltage for optimal performance. Voltage drop occurs when electrical current flows through a conductor, such as a wire, and encounters resistance, causing a reduction in voltage at the load end of the conductor. Excessive voltage drop can lead to various problems, including reduced lighting intensity, motor overheating, and malfunctioning electronic equipment. The NEC provides guidelines for limiting voltage drop in branch circuits and feeders. The recommended maximum voltage drop is 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the constant for the conductor material, which is 12.9 ohms for copper and 21.2 ohms for aluminum, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. Several factors can affect voltage drop, including the length of the conductor, the size of the conductor, the current flowing through the conductor, and the type of conductor material. Longer conductors, smaller conductors, higher currents, and conductors with higher resistance will all result in greater voltage drop. To minimize voltage drop, you can use larger conductors, shorter conductor runs, and conductors with low resistance. You can also use voltage drop calculators to determine the appropriate conductor size for a given application. Proper voltage drop calculations are essential for ensuring the safe and efficient operation of electrical equipment. When installing electrical wiring, it is important to choose the correct wiring method for the application. The NEC specifies various wiring methods, including non-metallic sheet cable or NM cable, rigid metal conduit or RMC, electrical metallic tubing or IMT, and flexible metal conduit or FMC. NM cable is commonly used in residential wiring and is suitable for dry locations. RMC is a heavy-duty conduit that provides excellent protection for wiring and is suitable for both indoor and outdoor locations. ENT is a lightweight conduit that is easy to install and is suitable for indoor locations. FNC is a flexible conduit that can be used in tight spaces and is suitable for both indoor and outdoor locations. The choice of wiring method depends on several factors, including the location, the environment, the type of wiring, and the budget. It is important to consult the NEC and local codes to ensure that the wiring method is appropriate for the application. Proper wiring methods are essential for ensuring the safety and reliability of electrical installations. When working with electrical panels, it is important to follow safe work practices and to use appropriate PPE. Electrical panels contain live electrical components and can be dangerous if not handled properly. Before working on an electrical panel, it is important to de-energize the panel and verify that it is de-energized using a voltage tester. It is also important to lock out and tag out the panel to prevent it from being accidentally re-energized. Never touch any exposed electrical components in the panel. Always use insulated tools when working in an electrical panel. If you are not qualified to work on an electrical panel, hire a qualified electrical contractor. Electrical panels are a critical part of the electrical system, so it is important to maintain them properly. Regularly inspect the panel for any signs of damage or corrosion. Make sure that all connections are tight and that all circuit breakers are properly labeled. If you notice any problems with the panel, have it repaired by a qualified electrical contractor. Proper maintenance of electrical panels is essential for ensuring the safety and reliability of the electrical system. Understanding the service entrance is essential for understanding the electrical system. The service entrance is the point where the electrical power enters the building from the utility company. It typically consists of a service drop or service lateral, a meter, and a service panel. The service drop is the overhead wires that connect the building to the utility pole. The service lateral is the underground wires that connect the building to the utility transformer. The meter measures the amount of electricity that is used by the building. The service panel is the main electrical panel that distributes the electrical power throughout the building. The size of the service entrance is determined by the electrical load of the building. The NEC specifies the minimum size of the service entrance conductors and overcurrent protection devices. It is important to ensure that the service entrance is properly sized to handle the electrical load of the building. Proper service entrance design and installation are essential for ensuring the safety and reliability of the electrical system. In summary, when dealing with electrical installations, it is important to consult the NEC and local codes, follow safe work practices, and use appropriate PPE. It is also important to hire a qualified electrical contractor for any work that you are not qualified to do. Electrical safety is paramount, so it is important to take all necessary precautions to protect yourself and others. Always remember that electrical work can be dangerous, so it is important to be careful and to follow all safety guidelines. By understanding the principles of electrical safety and following safe work practices, you can help to prevent electrical accidents and ensure the safety of yourself and others. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical contractor or engineer for specific recommendations regarding your electrical system.